what we'd like to do here is to work through an example of finding a directional derivative. The function I've chosen, if f of xy equals xy, the point I've chosen is 10, 5, and you still have to choose a direction of a chop. So I'm going to say in the direction of 3a plus 7j. Just a reminder of where this comes from. This is in the last two videos, I think, but we'll just see how it goes. Right. The idea is you zoom in on the graph until it looks linear. You're at a point, but instead of chopping west-east or south-north, you chop in a different direction, like this. Now, if I chop a surface like this, I'm still going to get a curve, just like I got a curve if I chop this way or if I chop this way. However, the run is not as easy, right? The slope we're looking for, we can certainly estimate that by the change in the z values between the contours. That should be the rise divided by the run. We'll worry about the run in just a second. I'm going to write down this is delta z. What's the run going to be? Well, when we went west-east, the run was just the horizontal distance from this point to this point. When we did chops that were parallel to the y-axis, we just went straight up, and it was just delta y. But the problem is that we want is now not the distance in the plane between these 2 points, and not the distance in the plane between these 2 points, but the distance in the plane between those 2 points. And so what we do, right, is we just draw it like this. This was delta x, that's how we labeled it before. This is delta y, that's how we labeled that before. And what we're going to get right here is going to be delta x quantity squared plus delta y quantity squared. Now that's as much as the graph can actually help us. And I need the space. So what are we going to do? Right now, if someone says, look at this function up here, this is not helpful. However, we do have a formula that estimates delta z. Like I say, it's one of the most important formulas we have this entire semester. That delta z is approximately equal to fx delta x plus fy delta y. And you should know where that comes from just on a regular plane. So I'm going to get delta x quantity squared plus delta y quantity squared, like that. And again, our linear algebra needs to be strong enough that we can recognize the top as being the dot product of two vectors. It's the dot product, let's write it down here, of fx, fy. You can see, by the way, that both partial derivatives are involved when we chop in a direction that's not west, east, or south, north, right? This is going to be delta x. This is going to be delta y, and the whole denominator is just the square root of delta x quantity squared plus delta y quantity squared, like that. Now, what is this? Well, it's got lots and lots of notation. This vector right here, the vector that we get just by taking the partial derivatives and lining up in a vector, is called the gradient vector. The notation for that looks like an upside down delta, looks like f. What is this? Well, we know that delta x, delta y was the vector and that chopped from one point to the next. But we're dividing by its length. So what we're getting is a vector that's pointing the right direction but has unit length. So what we're getting is that's the formula that we're going to be using for a directional derivative, not just a partial derivative. It is a directional derivative, so we need to make a vector out of the partial derivatives. We need a unit vector that's pointing in the correct direction, and then we need to dot the two. All right, let's look at the problem at the top. Now the ingredients are, I'm supposed to have the gradient vector, so let's calculate that first. The gradient vector at 10, 5 is the vector we get by taking the partial derivatives. The partial derivative of this with respect to x is just 1 over y. The partial derivative with respect to y, and we've done this several times this semester, is minus x over y squared, like that. And that's a formula for the gradient at any point. I want to plug in the point 10, 5. And when I do, I think I get 1/5 up here like this. I get minus 10 over 25. I think that's minus 2/5. So this is the gradient vector at the point that we're interested in. Tomorrow we'll start looking and saying, okay, I know how to find the gradient vector. What does it mean? But at the moment, let's just use it. I also need my unit vector. My unit vector should be a vector in the direction of the chop. Well, they gave us that. That's 3, 7. But that's not a unit vector. The length of this vector, I think, is the square root of 58. So we actually have to divide by the square root of 58 to get our unit vector. And then our final answer, now by the way, it's the notation they use for directional derivative is fu. Now fx is partial derivative with respect to x. That's really just a chop in the I direction. Fy is a chop in the j direction. This is clearly not either of those. So we want the directional derivative at 10, 5, which means we're standing on that graph at the point 10, 5, and we're chopping in the direction of 3, 7, and we want the slope. So what we're going to get here, I think, is 1/5 here, and minus 2/5 is here. And then we're dotting that with 3, 7. And then when we're all done, we're dividing by the square root of 58. Let's see here. This is going to be 3/5 minus 14/5. I think that's minus 11/5. Minus 11/5. So we just dotted the two vectors, and now we divide by the square root of 58. And if we want, we can write that a little shorter. Not a whole lot more helpful. Minus 11 over 5 times the square root of 58, like that. Now the square root of 58 is like 7.5, 7.6. So the bottom is roughly 35. So this is roughly minus a third. So it's going down, but not too quickly. That's it. That's our example.